All righty.
Uh, I have a question about the Vesper lab,
Yes.
and it's more specifically about the molecular geometry part,
Okay.
and just what you want us to do with that.
What did I ask? I can't remember.
It just says molecular geometry. Draw the geometry for each. Describe the molecular geometry and show the bond angles.
Okay, we'll be doing a problem just like that in a little bit.
Oh, all right.
So that'll answer the question when we get to the sample problem.
And then I just have one more question about that. How would I know with like a one of the linear ones if it's bent or not? Like, because I know the H2O one is bent, but
Okay, so the first thing I'm going to say is that's not an appropriate question because when you say
oh,
which of the linear ones is bent means that they're not linear.
oh,
So,
I guess that
however,
makes sense. Yeah.
what I think you're asking is if I draw a Lewis structure that looks linear, how do I know whether or not it's bent or really linear?
That's what I'm asking. Yes, sorry.
Yeah,
No, I worded
that's
the question wrong, but that's what I'm asking.
that's the question. So I want to make sure we put the correct question out there, and we'll be seeing that in some examples also.
Oh, well, alrighty then.
Okay.
Yes, we'll just wait. Yep, that's the only questions I had. So,
Okay, great. How about you, Jackie? Anything?
I kind of just had like a similar question. Like, I wasn't sure exactly what's the main differences between like an electron pair geometry diagram and a molecular geometry diagram.
They're not at all different if there aren't any lone pairs on the Lewis structure. But if there are lone pairs, they are different.
Okay.
So let's take a look at some of those right now, okay? But before we do that, I promised you that we would take a look at resonance structures for Lewis structures. And that's where we would pick up from today. So I want to take a look here at the Lewis structures or all resonance structures for nitric acid, okay? We'll skip A and we'll do nitric acid. So here's a nitric acid. And you guys can see what I'm writing. Is that correct?
Yeah.
Okay, great. Nitric acid is HNO3. And this is formed when you take an H plus and you add it to an NO3 minus. And we saw that back in the old acid chapter. So really, this is going to be the Lewis structure of the nitrate ion plus a hydrogen ion. So if we look at the nitrate ion, or the Lewis structure, if you will, of the hydrogen ion, it's simply that. Because a hydrogen atom has one dot on it, so a hydrogen ion has no dots on it. For the nitrate ion, we're going to have 5 electrons for the nitrogen, 18 for the oxygens because they get 6 each because they're in group 6A, and plus 1 for the negative charge for a total of 20. Let's see, I got to do this in my head. Plus 6 is 24 electrons. Okay, so the nitrate ion is going to look like this to begin with. 3 oxygens around it, and we're going to put lone pairs on each oxygen until you get to 8. And here you'll see that there's no octet. Now it turns out that most period 2 atoms, you want to get an octet on the atoms. The exceptions would be boron and beryllium. You don't need octets on boron and beryllium, but you want octets on carbon, nitrogen, oxygen, fluorine, and neon. So here we have no octet, and here we do have octets. So what would we draw for the correct structure? Well, we have to take a lone pair and make it into a bond. But we have 3 choices here. We can take a lone pair from the oxygen to the left, the oxygen to the right, or the oxygen up above. So which one do we do? And the answer is you do each one of them, one by one. So there are 3 resonance structures here. Here's one of them. And now each atom has an octet, and that's good. But there are two more resonance structures, and you indicate resonance structures with a double-headed arrow. So you might be asking yourself, why are we doing this? Because they look exactly the same. I could just take this molecule and flip it, and it would be that one. And the answer is, they're not exactly the same. The idea of resonance structures is this nitrogen is this nitrogen, and that's obvious. There's only one nitrogen. But this oxygen is, in fact, this oxygen. They are the same. So in this resonance structure, this oxygen has a double bond, and this one, it has a single bond. But it's the same oxygen. So does it have a single or does it have a double? Turns out neither. And here is the third equivalent resonance structure where the double bond is to the oxygen up above and a single bond here. So again, this oxygen here, which I'm going to put a little X inside of it, that's exactly the same oxygen in all three structures. And it turns out that you don't have a double bond between this nitrogen and this oxygen. You don't have a single bond between the nitrogen and oxygen or a single bond. You have an average of all of these. So what is the bond order here equal to? Well, if it were just a double bond, the bond order would be 2. If it were just a single bond, the bond order would be 1. So if this is indeed the same oxygen, and it looks like sometimes it has a single bond, sometimes a single, and sometimes a double, what is the bond order? It's an average of all. So it's 4 bonds divided by 3 structures, which is a 1.33 bond. Or a lot of people just leave it as 1 1/3. What does that mean for the bond length? Well, it turns out that single bonds are much longer than double bonds. And this bond is actually not the length of a single bond, and it's not the length of a double bond, and it does not change its length where it goes single, double, or it gets longer and shorter. It's a set length. And the length happens to be closer to a single bond than to a double bond, which means it's more like a single bond, and that bond order actually fits. So what is the bond order here? It's also 1 1/3. And so each of these has a bond order of 1 1/3. And this molecule actually has 3 bonds that have exactly the same length of 1 1/3 bond order. And these are the resonance structures. So to get to resonance structures, you have to draw all of them. But we're doing nitric acid, we're not doing the nitrate ion. So let's just take a look at one of these resonance structures. We'll take a look at this one right here and see how this would form a bond to hydrogen. Now, what makes the most sense is when we add the hydrogen, we're going to make a bond to one of these oxygens, but one of these lone pairs is going to bond to that hydrogen. If a lone pair on this oxygen bonds to the hydrogen, this oxygen will have 3 bonds, and we don't like that. This oxygen only has a single bond. If we bond this one to the hydrogen, we'll then have 2 bonds to that oxygen, and we do like that. We could put the hydrogen on this one also, but there's no point. I'm just going to put it on there. And the reason there's no point is because if I put it on here, it'd be the same as putting it here. Now you'll notice that I am losing the bracket and the charge because the -1 charge and a +1 charge is neutral, and we don't use brackets on neutral molecules. So this is, in fact, a very good Lewis structure for this. Now, are there any resonance structures here? And the answer is yes. Let me show you what one of them is. Well, the only real one, I should say. So here it is. These are resonance structures, and we indicate that with a double-headed arrow. So here you're wondering, how did I get here? Well, let me show you how to get here from the raw initial info. So, whoops. So the first thing you have to know is that whenever you see these acids where you have hydrogen plus an element that's not oxygen plus oxygens, that element there is the middle atom. The oxygen's attached to that middle atom, and the hydrogen attaches to one of the oxygens. In this case, I put the hydrogen here on the left instead of on the right, but that's okay. Now, when I put lone pairs in here, that's what you get, and the nitrogen does not have an octet. So in order to get an octet on nitrogen, I need to take a lone pair and turn it into a bonding pair. So this is a question for you. Do I want to take a lone pair from this oxygen and turn it into a bond between oxygen and nitrogen so that the nitrogen becomes an octet? Do we want to take that lone pair and turn it into a bond? Yes or no? And the answer is no, because then you have 3 bonds to oxygen. How about between that oxygen and that nitrogen? Would we like to take a lone pair from this guy and turn it into a bond? Yes or no? Yeah. And, you know, I'm pointing at this one down here, but I usually like to take the one over here so that the result looks symmetrical. So it looks nice and symmetrical. We have an octet on nitrogen, an octet on oxygen, an octet on oxygen, and an octet on oxygen. And we also have the duet on hydrogen. So this looks beautiful. How about here? Could we take a lone pair from this oxygen and make a double bond to the nitrogen and achieve the same results? Yes or no? So the answer is yes. And it would look like this. And there you go. Okay, so these are resonance structures, and we put a little double-headed arrow to indicate it like that. Okay, so do you understand how these are basically the same thing? This is just this turned around. So this oxygen is this oxygen. This oxygen is this oxygen. So these are your 2 resonance structures. Now, this is a really good example to take a look at, Harry, and say, look at that. That looks linear when you have the hydrogen, oxygen, nitrogen, right? Looks linear. And in fact, this looks like a T shape with around the nitrogen. Is that correct? And the answer is no, neither is correct. So let's get the molecular geometry of both resonance structures. So what I'm going to do now is I'm going to draw both resonance structures again. Only instead of drawing one above the other, I'm going to draw them side by side. Okay, so we've got octets everywhere. These are great resonance structures. Let's turn them into molecular geometries. But to do that, we take the Lewis structure, find out how many pairs, get the electron pair geometry, and then get the molecular geometry. So when you're writing this down, LS stands for Lewis structure, PR stands for pair, EPG stands for electron pair geometry, and MG stands for molecular geometry. Okay? So we already have the Lewis structure here. It's this or this. Let's focus on this resonance structure on the left, and let's get the pairs. How many pairs does this oxygen have? 1, 2, 3, 4. So what I'm going to do for the oxygen is I'm going to do this, and I'm going to let you see that it has 4 pair. So the oxygen has 4 pair. Now, what about the nitrogen? How many pairs does it have? I'm going to use a different colored pen so you can see the pairs on the nitrogen. Here's one pair. That counts as a pair for the nitrogen. And the double bond counts as one pair. So the nitrogen has 3 pair. So when we get to the electron pair geometry, this oxygen is going to look like this, or this. Tetrahedral. 4 pairs tetrahedral. What is 3 pair going to look like? Well, the nitrogen is going to look like this, or this. We call that trigonal planar. So number 4, I'm going to go ahead and get the molecular geometry, and I'm going to incorporate all of these ideas into the molecular geometry. So I know my oxygen looks like this, and I'm going to draw my oxygen here, and I'm going to draw this going up to the hydrogen, and this going to the nitrogen. So you can see that this part looks like this part right here. And then on the wedge, I'm going to draw a lone pair, and on the dash, I'm going to draw a lone pair. So here, this is tetrahedral, but this is the shape of those 3 atoms. So here, if this is my arm, sticking straight up, what is the shape when I do that? We call it bent. So Harry, this is how we know when you have something drawn linearly here, that it's not really linear in the molecular geometry, because these lone pairs have an effect on the overall geometry. So this would be bent, and it's 109.5 because tetrahedral gives you 109.5 degree angles. Now, if I continue to draw this, and I've kind of made a mistake by drawing that there, I'm going to erase that. Not erase it so much as cover it up. Okay, so the nitrogen's got to be trigonal planar, and you can see I have my nitrogen drawn this way, but I could also draw the nitrogen this way. So I'm going to do it this way, and I'm going to have a single bonded oxygen here and a double bonded oxygen going down. Let me put in the lone pairs everywhere, and here we go. This is a nice 3D geometry where the oxygen is bent 109.5, and the nitrogen is trigonal planar 120 degrees. So this shows you how you can take a Lewis structure and turn it into a molecular geometry. Now, let's take a look at this resonance structure. How many pairs on the oxygen? This one right here. 4, right? If you agree, give me a thumbs up. Okay, so the oxygen has 4 pair. How many on this nitrogen? If you think it's 4, give me a thumbs up. If you think it's 3, give me a thumbs up. Okay, it's 3 pair. And this is my one beef with what's called VSEPR, is that VSEPR stands for valence shell electron pair repulsion theory. In VSEPR, pairs can be a lone pair. Pairs can be a single bond. Pairs can be a double bond. A double bond is a pair. A triple bond is a pair. Really what they mean when they say electron pair, they're saying regions of electrons where the electrons are kind of stuck together. So in a bond, they're stuck together. In a double bond, they're stuck together. In a triple bond, they're stuck together. So electrons that are stuck together in a certain region repel other regions of electrons that are stuck together. But that makes a heck of a long name for a theory. The theory that regions of electrons stick together and repel other regions of electrons that stick together. And if you put out the letters for it, it's got no ring to it. So VSEPR is what they came up with. All right, so 3, what is the electron pair geometry of this guy with 4 pair, tetrahedral? And what is the electron pair geometry of the nitrogen with 3 pair? It's trigonoplanar. So another thing I like about this molecule is you can see that the electron pair geometry for oxygen has a different name for the molecular geometry, but the molecular geometry is definitely influenced by the electron pair geometry. We don't pretend like these electrons aren't there. They are. And also you can see that sometimes the electron pair geometry has the same name as the molecular geometry. And what is the big difference between these two cases? And the answer is really simple. The oxygen has lone pairs and the nitrogen does not. So when you have no lone pairs, the electron pair geometry, the EPG, matches the molecular geometry, the MG. When you have lone pairs, they're different. Okay, so here, if we finish drawing this, we would draw something like this, more than likely. And you'll notice that the resonance structures have the exact same geometry. So I'm just going to put a little arrow there. Okay, any questions about this one? If you do, please ask. If you don't, give me a thumbs up and we'll move on.
So we would have to create like an electron pair geometry and molecular geometry diagram for like each of the resonance structures.
That's a great question. And I think it really depends. Like the sulfate ion has 4 resonance structures. And I think that if you draw the resonance structures, you can easily say that they all have the same electron pair geometry. Are you with me?
Yeah.
And if you draw all 4 of the molecular geometries, you're not going to learn anything new, except for that all of the atoms have the same molecular geometry. So you should draw for the Lewis structure all of the resonance structures. But for the electron pair geometry, it's going to be the same for all resonance structures. And the molecular geometry is going to be the same for each of those resonance structures. So just draw one electron pair geometry and say they all look like this, and then draw one molecular geometry and say they all look like this, with the caveat that, oh, the double bond moves around. Does that make sense?
Yeah.
Yeah, it's a lot less work, but so that I know you really understand it, I would like to see the resonance structures for the Lewis structures.
All right.
So this is the kind of information I would expect to see. You see what I have blocked off on the left?
Yeah.
Both resonance structures, one electron pair geometry, and one molecular geometry. Heck, for the molecular geometry, you could even do, or excuse me, for the electron pair geometry, you could even do something like this. And that shows the molecular or the electron pair geometry around each atom. You don't have to separate them out like I did here. Okay, but I find it a little bit easier to separate them out than think about how these pieces kind of come together like this. Does that make any sense?
Yeah, thank you.
Yeah, handle the atoms one at a time and then put them together.
And oh wait, just one more question with that.
Sure. Can you put that
And
back?
so yeah, and so if the H to the oxygen to the nitrogen, if the oxygen didn't have those two, the two lone pairs, it would just be linear. Just
This?
Yeah,
Yes.
just if the oxygen didn't have, say the oxygen doesn't have those two lone pairs with the H to the O to the N, it would just be linear.
That's correct.
Okay.
So let's take a look at some other molecules here. Let's see what I've got next. So I've got a bunch of molecular geometry ones. We did some formal charge stuff last time, right? So let's skip this. Well, let's do this one formal charge one where it says determine the formal charges on each atom. So this is not about molecular geometry. It's just about formal charge. So let's take a look at this one here because it's interesting. And we'll take a look at this one here. It might be a little interesting. Actually, let's do this one here because it's an anion. So we're going to do a formal charge problem. And this is a reminder of how to get formal charges. So we're going to do BH4 -1. To get formal charges, you do need to know the Lewis structure. So I'm missing something from this Lewis structure. And what I'm missing is any indication that it's an ion. So how do we indicate ions? Bracket and a negative. So we're going to assign formal charge two ways. We're going to do the deconstruction way, where we deconstruct this, and then we'll do it the calculation way. So when we deconstruct it, the boron gets half of each bonding pair, so that means 1 electron from each bond, and the hydrogens get 1 electron from each bond. So we compare what we have here compared to what the atom looks like when it has all of its valence electrons. And hydrogen, being in group 1A, has 1 valence electron, and boron, being in group 3A, has 3 valence electrons. So how does this hydrogen look to this compared to this? They look exactly the same, so the formal charge is 0. Now this boron, if it were neutral, it'd have 3 valence electrons, but here it has 4. So what happens to the charge on something when it gets an electron? It's a negative. So the formal charges here are 0, 0, 0, 0, and a -1. Now, if we do the formula way of calculating them, the formal charge on the boron is equal to the number of valence electrons in the periodic table minus 1/2 of the non-bonding electrons plus, oops, excuse me, let me get rid of that 1/2, minus the non-bonding electrons plus 1/2 of the bonding electrons. So that's the formula. And you can see why I don't like the formula, because you have to think about, oh, where do all the numbers go? Here, I just like deconstructing it and looking and comparing. So boron has 3 valence electrons. The non-bonding electrons here are 0. The bonding electrons are 8. So you get 3 minus 4, or this is supposed to be a plus. So you get 3 minus 4, which is -1. I won't show you the formula way for doing the hydrogen. You can figure that one out. But either way you slice this, you get a -1 here and a plus or a 0 on each hydrogen. And as far as formal charges go, that's pretty good for a Lewis structure. When you have a charge on the particular ion, you're going to have a formal charge that's not 0. But we've got 4 that are 0 and only 1 that's not. That's pretty good. Now let's take a look at this guy, SCO. We've got 6 electrons for carbon, or sulfur, I'm sorry. 4 for carbon and 6 for oxygen for 16 electrons total. So this thing's probably going to look like this. I didn't show you how I got there, but you're expected to be able to get here. This looks a lot like CO2, which is this. And in fact, these guys are considered to be isoelectronic because the distribution of valence electrons is exactly the same in both. Okay, so what's the formal charge on this carbon? Well, if I deconstruct, it ends up with 4 electrons. Carbon is in group 4A. It should have 4 electrons. Formal charge is 0. If I deconstruct this guy gets 6 electrons. The 4 here plus half of these, which would be 2. And an oxygen with 6 electrons is a neutral oxygen atom. So those are the formal charges here. So this is why we really love this structure, is the formal charges are all 0. We also talked about this last time, that when you get the formal charge you want, a 0, you usually have the number of bonds you want also. Oxygen normally makes 2 bonds, carbon 4, and sulfur 2. Okay, so that being done, that's a couple of formal charge things. Now let's take a look at this one here. This says, draw a Lewis structure, describe the electron pair geometry and molecular geometry around the central atom. Okay, so that word describe, does that mean draw? Not necessarily. A drawing could describe it. We all know a picture's worth 1,000 words, but you also could just use a name. So let's take a look at a few of these. NH2Cl, 5 plus 2 plus 7, for a total of 14 electrons. You're going to put nitrogen in the middle because it's the least electronegative other than hydrogen. Hydrogen can't be in the middle. And when we take a look here and count electrons, 2, 4, 6, 8, 10, 12, we need 2 more. We put them on nitrogen. So here, how many pair on the nitrogen? We've got 4 pair, which means the electron pair geometry is tetrahedral. So I can even show you the 4 pair by doing this. 1, 2, 3, 4. 4 pair. Now, if I know that it's going to be tetrahedral, I know it's going to look something like this. So that means I'm going to have to put the lone pair on one of these places, and I'm going to have to put the hydrogens and the chlorine on the other places. So when I get to the molecular geometry, the thing that makes the most sense is to do probably something like this. And what do we call this geometry? Here, this is tetrahedral, and the angles are 109.5. Here, this is called trigonal pyramidal, and the angles are about 109.5, because the angles on the electron pair geometry are going to be the same as the angles on the molecular geometry for our guess. The bond angles are not 109.5. They're a little bit less than that, but 109.5 is a really, really good guess. So here we've described the molecular or electron pair geometry, and we've described the molecular geometry. All right, any questions on that one, or are we okay? Are you okay there, Harry? Okay, now I'm going to pause for just a moment the recording. All right, can you see my hand? Give me a yes if you can. Okay, great. So let's do some more of these. Let's take a look at this molecule here. And honestly, on the exam, I'm not going to ask you to just describe it. I'm going to ask you to draw it. Okay? So let's take a look at this guy. We want to get the electron pair geometry and the molecular geometry. And they tell us that in this case, oxygen is central. Okay? O is central. So we have 14 for the 2 chlorines, 6 for the oxygen for 20. We're going to put oxygen in the middle and the chlorines on the outside. When I get my octets on my chlorines, I've used 16 electrons. And now I have 4 more to use, so I'm going to put the rest on oxygen. So do we see how this Lewis structure looks linear? However, we're going to do these 3 things. Basically, once you get the Lewis structures, we want to do how many pair, what's the electron pair geometry of those pairs, and then what's the Lewis or molecular geometry. So here, how many pair on the oxygen? 4 pair. So that means that the electron pair geometry is going to look like this. What's the name of that electron pair geometry? Tetrahedral. What are the angles between the pairs? 109.5. Sounds like a radio station. 109.5, where they play tetrahedral music all day long. Now, for the molecular geometry, we want to put the lone pairs in place and the bonding pairs in place. And to me, this makes the most sense. Put the bonding pairs here and the lone pairs here. And then you get this. And what do we call this geometry where the lone pairs don't stick out into space and make this tetrahedral, but they're kind of like a little cap on the oxygen? And the answer is, we call this bent, and the angle is about 109.5. So again, here's where a linear Lewis structure ends up being bent. Are there any questions here? Are we okay on that one? Okay, let's do something a little more difficult. Let's do this guy. This is called the thiocyanate ion. So to do this guy, we've got 6 plus 4 plus 5 plus 1. The negative counts as 1 electron. When we add this up together, we get 16 electrons. And so for this one, it turns out that this looks pretty good. But there are resonance structures. So clearly, if I have a double bond here and a double bond here, that must have been because I had a lone pair on the nitrogen that I turned into a double bond and a lone pair on the sulfur that I turned into a double bond. So if that's the case, I could have turned 2 lone pairs from nitrogen into a double bond and none from sulfur. And I could have done the same for the nitrogen. No lone pairs into a double bond. So these are my 3 resonance structures. Let's evaluate these by formal charge. Here it's a 0, here it's a 0, here it's a -1. Here it's a 0, here it's a 0, here it's a -1. And here it's a 0, here it's a +1, and here it's a -2. So if you look at these 3 resonance structures, are there any that we're going to say, no, nope, not going to happen? It's this one. And the reason is because of that formal charge of -2. Formal charges of -1, that's fine. Formal charges of +1, that's fine. But we draw the line at 1. When you get a formal charge of -2, unless you have a really good reason to have that, meaning you don't have any other resonance structures, unless you have a really good reason to have that, you get rid of it. So these are the 2 resonance structures here. Now, let's take a look at the electron pair geometry around carbon. So for carbon, how many pairs in this resonance structure? 2. How many in this resonance structure? 2. So Jackie, you asked before, do we need to do the electron pair geometry for all of these? And the answer is it's going to be the same for both. Now, this is the electron How do I do that? I said electron and I drew an M. Electron pair geometry. So for the molecular geometry, if we want to draw one of them, it just looks like this. Oops, that's supposed to be a sulfur. Now, if we wanted to draw the other one, it would look like this. They're both linear, 180 degrees. And this is linear, 180 degrees. So, Harry, this is the example where when we draw the Lewis structure, it looks linear. And in fact, the molecular geometry is also linear. So why is the Lewis structure match this? It's just because of the number of pairs. Are you okay with that, Harry? All right. Are we okay with that, Jackie? So notice I'm naming it, describing it, I'm drawing it, and I'm putting the bond angle. So here, the molecular geometry, this is the drawing. And this is the description, and this is the angle. You want all three. Let's do another one here. PO4 3 minus. So there's 5 electrons for oxygen. There are 6. I said that incorrectly. There are 5 electrons for phosphorus. There are 6 electrons for each oxygen with 4 total. 4 times 6 is 24. And we add 3 electrons because of the charge. So here we're going to get, let's see, 32 electrons. Did I do that right? Okay. So let's draw the structure of this. Phosphorus in the middle, oxygen's on the outside. 2 on each. So from an octet point of view, how does this look? Looks really good, doesn't it? Everything's got an octet, and we've used 32 electrons. Let's evaluate it from a formal charge point of view. The formal charge on each of these oxygens is -1. And I'll show you the formula way of getting that. Formal charge on an oxygen with 3 lone pair and a single bond is going to be 6 minus 6 plus 1/2 of 2, which is -1. So another thing that we can do to get formal charges is it's really interesting. All of these formal charges plus the 1 on phosphorus should equal -3. So what does the formal charge on this phosphorus have to be to get a -3? And it's a +1, right? And that gives you the -3. So this isn't too bad, but what happens if we take a lone pair and make it into a bond? In this case, you have a -1 here, a -1 here, a -1 here, a 0 here, and a 0 here. So between these two resonance structures, which one's better? They all have 1s. This guy has no 0s. This guy has 2 0s. This one's better because it's got 0s. Okay. And you might say, well, why don't we just make double bonds with all the oxygens? And if you do that, you'll find out that you don't have very good formal charges on phosphorus. We could actually do one more. We could do this. So the formal charges here are -1, -1, 0, 0, and -1. So compare these two, which is better? And the answer is this one, because if you're going to have a negative formal charge, you want it on a more electronegative atom. And here, when we go from here to here, we take away a -1 from this oxygen and we put it on the phosphorus, which is not more electronegative, it's less electronegative. So we don't like this one. We don't like this one. This is best. How many resonance structures can we draw of this guy right here? Well, we could put the double bond there, or there, or there. So there's 4 resonance structures. So let's just take a look at one of those. And let's deal with the electron pair geometry around phosphorus and the molecular geometry. So phosphorus has 4 pair. What type of geometry is that? Tetrahedral. And that's 109.5. And what's the molecular geometry? It's also tetrahedral. Okay, so are we okay with how we got to the final answer here? And we could here also put plus 3 more resonance structures. All right, let's try some more now. I'm looking for another good one here. All right, so here's another one, molecular geometry. Actually, I want to do one that's not here. I'm going to look something up on the internet. Let's see. No, that's not the one I want. All right. Let me see if I can show you something here in just a minute. Here we go. You can't see this right now, but you will be able to see it in just a moment. Okay, so I'm going to change my share screen with you. And for this one, you're going to have to talk to me. Okay, so you should unmute yourself. So this is a molecule called EDTA, which is used to remove toxic metals from the blood. That M in the middle you see is a metal. So this molecule is very water soluble. It binds to metals. And because it's water soluble, you essentially pee it out. So you can remove heavy metals this way. So the question I have to ask for you is this. If each of those set of dashed red lines is a bond to the metal, how many pair do you see? So don't say it out loud. Come up with an answer. When you have an answer, give me a yes or give me a thumbs up. So the question is, how many bonds do you see to the metal? Give me a thumbs up when you have an answer. Okay, so give me your answer. 1, 2, 3, now.
6.
6.
Jackie, you're a little slow there.
Uh,
It
well,
is
I did say
6.
6 though.
It's
Yeah.
6. Great. Next question. Based on 6 pair, what's the electron pair geometry called? Think of your answer. When you have your answer, give me a thumbs up. Based on 6 pair, what's the electron pair geometry called or named? Give me a thumbs up when you're ready. Okay. It is called 1, 2, 3 now.
Octahedral?
Octahedral.
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 Correct. Now, based on the octahedral, what are the bond angles considered to be? Give me a thumbs up when you have your answer. And there are actually 2 bond angles. So starting with the smaller bond angle, those bond angles are
90.
90 degrees.
and
180.
180. That's correct.
That's 90.
Now, for the molecular geometry, what would that be called? Are there any lone pairs?
No.
Each
Right.
line is a bond, so there's no lone pairs. So what's the name of the molecular geometry compared to the electron pair geometry?
Is it still octahedral?
It's the same thing, octahedral. What are the angles?
90 degrees and 180 degrees?
90 degrees and 180 degrees. Now imagine, if you will, do you see the bond from the metal going to that oxygen on the bottom?
Yeah.
Yeah.
What if that bond broke
Oh.
and the electrons ended up on the metal? So you have 5 bonds and 1 lone pair. 5 bonds and 1 lone pair. How many pairs is that total?
6.
6.
Still.
5 bonds and 1 lone pair. That's 6 pair. What would the electron pair geometry be?
Octahedral.
Octahedral. Now, what would the molecular geometry be?
Octahedral.
Octahedral.
Nope. When you have a
No?
lone pair, the
Oh,
name
is
changes.
it oh, geez, is it what?
Square pyramidal.
Oh,
Because those 2 nitrogens on the left and the 2 oxygens on the right would form the square. And that oxygen in the top would be the point of the pyramid. Are you with me?
right.
Yeah.
So square pyramidal, square pyramidal or square pyramidal. Now I'm going to change my share screen and I'm going to show you the metal plus the 6 bonds. Do you see that?
Yeah.
Are you with me there? So imagine if one of those bonds breaks and we end up with just a lone pair right here on the bottom. Do you see how that looks square on the bottom? And if we look at it from the side, it looks like a pyramid if we put sides on this.
Yeah.
So that's why they
Let's do
call it
that.
square pyramidal. And if you had another lone pair on this, it would be on the opposite side of the first lone pair because lone pairs really repel one another a lot. So this would have an electron pair geometry of octahedral. What would the molecular geometry here probably be called, considering that this is called triangular planar? What would this be called?
Is that the tetrahedral?
No, triangular planar. Tetrahedral means that it looks like, tetrahedral means it looks like that.
Oh.
So it's square planar.
Square planar.
Oh.
So what I'm trying to get you used to is the way they describe these shapes is supposed to help you remember them. And the shape itself is supposed to help you remember the description. Like, why is this one called tetrahedral? And the answer is, if you connect the purple, orange, and green dots on the bottom, it's a triangle. If you compare these three dots, it's a triangle. These three dots, it's a triangle. These three dots, it's a triangle. This thing is made out of 4 triangles, 4 sides that are triangles. Tetra, 4, hedral, side. Actually, hedron is side. Tetrahedral is a adjective. Okay, so I want to do a couple more things here that are going to help you with the test and with the quiz. Let's look at this one right here. Consider the following molecules in which are the most polar bonds found. So how do we judge polarity of bonds? We look at electronegativity. And when we look at electronegativity, I think you should memorize some electronegativities. And they are these. So when I say memorize them, you don't want to memorize them exactly. You want to have a really good idea. Electronegativity is a measure of how well you attract shared electrons. Since neon does not share electrons, electronegativity does not apply to neon. Fluorine is a 4O. It is by far the most electronegative element. Oxygen's a 3,5, nitrogen's a 3O, carbon's a 2,5, boron's a 2O, beryllium's a 1,5, and lithium's a 1O. So do you see how easy these are to remember? What do they drop by? They drop by half each time. Hydrogen is a 2,2. So that means it's more electronegative than boron, but less than carbon. So you should memorize those. So when they talk about the most polar bond, they mean the biggest difference in electronegativity. Now, to be able to do this, you actually have to have the structures of each of these. So I'm going to draw those really quickly. And I'm drawing the molecular geometry. Okay, there's the molecular geometry of each of the molecules that they're asking about. And the first question is, which has the most polar bonds? So the biggest difference. And you can see, I'll put chlorine here. Chlorine's a 3O. So between this, it's a difference of 3 or difference of 1, right? How about carbon and chlorine? It's a difference of half. How about carbon and oxygen? It's a difference of 1. How about oxygen and hydrogen? That's a difference of 1.3. What about nitrogen and hydrogen? That's a difference of 0.8. So this is the most polar. So any questions about which has the most polar bonds? Are we okay with that? Now, what you should know about electronegativity trends is that in a period when you go to the right, they're more electronegative. In a group, when you go up, they're more electronegative. So fluorine is more than chlorine, hydrogen is more than lithium. What do we expect for nitrogen compared to lithium? We expect nitrogen. What do we expect for sodium compared to lithium? We expect sodium to be even smaller than lithium. But the trend is not the same. It doesn't drop by 1.2 each time. Okay. Which of these molecules are nonpolar? So which of the molecules are nonpolar? Nonpolar means that you don't have, well, polar means this, that when you look at the molecule as a whole, you have a slightly negative side and a slightly positive side. Nonpolar means you don't have this. So how does this arise? It arises when you have a really electronegative atom on one side of the molecule or the other. So here, if we take a look at this, do you see how the more electronegative atom oxygen is on this side of the molecule, making it slightly negative and the other side slightly positive? Here, the nitrogen is on one side, that makes it slightly negative and slightly positive. But the difference between electronegativities is very slight. So this is just slightly polar. And this is how we draw that. The longer the arrow, the more polar it is. You always put the plus side of the arrow next to the slightly positive side and the pointy side next to the slightly negative side. And you see how when I draw my line through the molecule, I try and draw my arrow perpendicular to that line. Are you with me there? So here, is there a more polar atom between these two? You bet, the fluorine. So where would I draw the positive part of my arrow? Right here, and it would go perpendicular to that line, to the fluorine, and that's the molecular polarity. Now, what about this guy? Does this have a molecular polarity? This one is actually nonpolar. And the way the book kind of handles it, and the way I like to handle it too, is we could say that that bond is polar, where the oxygen is more negative and the carbon's more positive. And we could do that for the other side too. And with these arrows, I like to say, I like to pretend that you're walking the dog. So you're that carbon, and this is a leash to a dog. And you're this carbon, that's a leash to that dog. If you're holding two dogs and they're pulling you in opposite directions, and both dogs are exactly the same kind of dog, which way are you likely to go as that carbon atom? And the answer is no way. So that means it's going to be nonpolar. If you contrast that to this, and I draw the arrows in like this, and we walk the dog, in this case, these dogs are nipping at your heels. So these are little chihuahuas nipping at your heels. Which direction are you going to move to get away from those chihuahuas? And the answer is you're going to move in that direction to get away from those chihuahuas. So that's the molecular polarity. So I like to do what I call walking the dog, where you put little arrows in for the bond polarity, and then you add them up like walking the dog. Oops. So look at this molecule on the end here. Does this have molecular polarity or is it nonpolar? So you're walking 4 dogs. Would any of those dogs tend to pull you in one direction because it has a greater electronegativity? And the answer is no. So this is nonpolar. So you guys kind of okay with assigning polarity? I'm going to clear you and make sure you give me a thumbs up. Okay, then. Let's look at bond order and bond length. Actually, let's look at bond strength. There's 2 problems here that we can look at. So let's look at the first one. Consider the carbon-oxygen bond in formaldehyde and the carbon monoxide, or end in carbon monoxide. In which molecule is the CO bond shorter? In which is it stronger? So we need to have structures for these. So this is the one for formaldehyde. And this is the one for carbon monoxide. So here's a real weird one because carbon only has 3 bonds, but it still has an octet. Okay, so here, the carbon-oxygen bond order is equal to 2. So when you have a double bond, the bond order is 2. When you have a triple bond, the bond order is 3. When you have a single bond, the bond order is 1. So let's answer which one is stronger. This one is stronger. More bonds, the harder it is to break, the stronger it is. Let's talk about shortness. This one's shorter. Turns out that more electrons makes a shorter bond because you want to think about those electrons as like rubber bands pulling things together. So, do you understand why the CO bond is shorter? If you do, give me a thumbs up. Shorter because it has more bonds. Can you tell me why it's also stronger? And the answer is more bonds, stronger. So I want to end with this last one here. Ethanol can be made by the reaction of ethylene and water. Here's the reaction. Use bond association enthalpies to estimate the enthalpy chart change for this reaction. So I'm going to write the reaction down. And there is an example of this in the lecture, but this is a different example. And it'll give you a better idea of what to do, maybe. So to be able to do this, you first have to have Lewis structures. I'm trying to draw these so you actually have an idea of the geometry. Now, this here, the CH3, it's going to look like this. This is supposed to be CH2. I made a mistake. Okay, to do this problem, the heat of reaction is equal to the sum of the bonds broken. And I should say it's equal to the sum of the enthalpy of bond breaking minus the sum of the enthalpies for those that are formed. So the reason this is a negative is that when you break a bond, you have to put energy in, and that's endothermic. But when the bond reforms, it's exothermic. So that's why you have a negative here. So if we take a look at everything that's happening here that are bonds that are being broken, you can see that we have 1, 2, 3, 4, 4 carbon hydrogen single bonds. I'm going to get rid of that. Plus 1 carbon-carbon double bond. Plus 2 oxygen-hydrogen single bonds. So what I'm doing is I'm deconstructing each of those and I'm finding out what bonds do I have. I've got 4 carbon-carbon single bonds, 1 carbon-carbon double, 2 oxygen-hydrogen singles. Now, what do we have here in the product? We have 1, 2, 3, 4, 5 carbon-hydrogen bonds. We have 1 carbon-oxygen bond. And we have 1 oxygen-hydrogen bond. So when we look up these values in our book, and these values are on page 391 in the 10th edition, we get this. 4 times the carbon hydrogen bond is, actually, it's not that page, it's a different page. It's on page 392. So carbon hydrogen bond is 413 kilojoules. A carbon-carbon double is 610 kilojoules. And an oxygen-hydrogen is 463 kilojoules. And then we already know that the carbon-hydrogen is 413 kilojoules. A carbon-oxygen is 358. And then a oxygen-hydrogen is 463. So those should be the same right here. So when we total these, I'm going to do the ish. When we double that, we get around 900 and, actually I'm doing this, 926, right? Plus 610 is 1,536. Plus 4 times that is 1,652. So here we get a total of 8831. And here we get 5 times 413, which is what, 2,000, and 5 times 13 is 65. And 358 and 463. So 6, carry the 1. 7, carry the 1, 8. So minus 2876 kilojoules. So the enthalpy of this reaction is going to be the difference between these two, which is going to be 2, 1, 312 kilojoules. Oops. So you can see it all. Now, what would have happened if this were a 2 here and this were a 2 here and this were a 2 here? Naturally, we're not going to have that. But the question is what if you had a coefficient of 2? How many hydrogen-oxygen bonds would you have? Here we have 2. How many would you have in 2 of these guys? You'd have 4. So you need to worry about these guys when the coefficients aren't 1. You need to think about that. Is that clear? So just for fun, so if we wanted to do this one, we would have this, this, and this. So when we do the enthalpy of the reaction, and we wanted to look at the bonds formed versus the bonds broken. So we need to break these guys up. So we put energy in. You would have 2 hydrogen-hydrogen bonds. Why do I have 2 hydrogen-hydrogen bonds when here there's only 1? So go ahead and unmute yourself and tell me why I have a 2 here when there's only 1 there.
Does it have to do with the H2?
It has to do with the coefficient.
Oh,
Because really, when I draw this, that's what one of these looks like, right?
right.
What's the other one look like?
Oh, the same.
The same. So how many bonds do I have to break?
2.
Okay, and over here, how many hydrogen-oxygen bonds do I form when I make 2 H2O?
Do you form 2 of them? Or 4 of them? Sorry,
4 of them.
4 of them.
You see how coefficients make this tricky?
Yeah.
So this, if we finish it, it'd be 2 of these, plus we have to break 1 of those. And then we have to form 4 of those. So this is what I was meaning when I said you need to watch out if you have coefficients here. So do you understand now why that's a 2, that's a 1, and that's a 4? Are we okay with that? Give me a thumbs up if you're good on that. Okay, we're not going to finish this problem out, but you're going to see something like that on the exam. Although it's going to be tough to put something like that on the quiz. I'd have to be really simple to be on the quiz. So your quiz will be tomorrow. The exam will be Friday. And remember, you get the 3x5 card for the exam. Any questions? All right, turn your mics on and say goodbye.
Bye, guys.
All right, remember you can Zoom on Friday before you take your exam also.
All right.
All right.
All right, bye-bye.
Bye.